So in this video, we're going to look at some series tests for determining whether or not our series converges or diverges. Now, we're going to start with the simplest test and then the what I consider the next simplest test. The simplest test is sometimes referred to as the nth term test or the test of divergence, the divergence test, something like that. And the reason for calling it the divergence test is that it is a test that clearly determines whether a series will diverge or not, but it does not really tell you if the series will converge. So there is a clear condition that will definitely mean the series diverges, but there is some ambiguity if something else occurs. And we have to be careful with this because the second test we're going to look at is the alternating series test. It is very similar to this test, but its conditions are going to be a little bit different. So let's look at some specific examples. Now, for any series, it doesn't matter where it starts, but if the limit of the sequence of the terms does not go to zero, the series will diverge. Now, that is the key claim here, is this test cannot be used to show convergence. It can only be used to show divergence. So if you are looking at a series and you think, okay, the terms don't go to zero, then you can use this test. It's very simple. And then you can say it diverges and move on. If the limit, however, does go to zero, it turns out that some of them will converge and some of them will diverge, and we can't use this test to tell. So let's look at some specific examples. The harmonic series is a P series where P is 1. This is the form of 1 over n for our terms of our sequence. And if we let the limit of n go to infinity, we get 0. But we can see with other tests that this series, in fact, does not converge. It, in fact, diverges. Whereas if we have a very similar series with 1 over n squared, this limit does go to 0. And using the same test that we use for the harmonic series, we can actually show using the integral test, or the P test, the P series test, that this will, in fact, converge. So we haven't established that, but we will as we do some more examples in another video with an integral test and the P test. We will be able to see that, in fact, even though both of these limits are 0, they actually behave as a sum very differently. On the other hand, in our third example, we have n factorial over n squared. This is very clearly going to diverge. If you look at the limit's actually infinity. The factorials will grow much faster than the square will. And these values will continue to get larger and larger and larger, and therefore it's clearly going off to infinity. So the nth term test is a good test to start with if you suspect that it's going to diverge. But you do have to be very careful. If you get a limit of 0, that doesn't mean anything, and you need to try another test. Now, this test often gets confused with the second example test that we're going to look at, which is the alternating series test. Now, the alternating series test is going to have a component of the formula that is alternating, so that terms will be positive, negative, positive, negative. And so they are going to change sign. So when you add them up, they're going to partially cancel each other out. Now, there are some very specific conditions for this test, but often they're really covered by the fact that the limit exists or it doesn't exist. You need a sequence that is decreasing, for instance. But if your sequence is increasing, its limit is definitely not going to be 0. So the alternating series test is going to agree with the divergence test or the nth term test. If your limit is not 0, then the series will diverge. That is going to be true for both of these tests. But the alternating series test, because of this alternating component, it can be a little bit more powerful, and it can say that if this limit actually is 0, then the series will converge. The nth term test can't do that, but the alternating series test can because of that alternating component. Now, that's very powerful, but it's very easy to get this confused with that previous example. If we look at the alternating harmonic series, which is just the harmonic series, but with a sign change, then this is going to satisfy all of our conditions. The terms are going to get smaller as we go, so the absolute value of them, so without the alternating component. And the limit is going to go to 0. And therefore, we can say that this alternating harmonic series is going to converge. Now, one thing we're going to see later on is that you're not going to be able to test alternating series using the integral test in the same way that you can series that are very positive. So just kind of keep that in mind. I will do another video later on that will talk about the error formulas for the alternating and integral test together. This second example is a little bit more disguised than the previous one. It has -3 to the n or -3 to the n plus 1. We can pull out the -1. Now, one thing to kind of keep in mind about the n versus n plus 1 and the exponent here, it's just a matter of what the value is. Is it positive or negative when you plug in your first value? So that the only difference here is that we're saying that when n is 1, this is positive, as opposed to when n is 1, the term is negative. So that's the only difference between -1 to the n and -1 to the n plus 1. Now, again, we have n factorial in the denominator, and we can actually see that factorials are going to grow faster than powers of 3. And so this will be a decreasing sequence, and the limit will go to 0, and therefore we can say that the series will converge. Now, in some cases, we do have to be a little bit careful. When you have -1 to the 2n or 2n plus 1, the squared here, this 2 is actually going to square the -1. And so it's actually going to be -1 in this case all the time. And so this is not an alternating series. This is an example that sometimes they throw into the textbook to see if you're paying attention. And so this is actually not an alternating series in this case. This value of this numerator is always -1. So you do have to be sometimes careful that just because it has a -1 with a power, that it's not necessarily always going to be alternating. There are ways that they can disguise it as non-alternating, but make you think that it's alternating. Now, this 1 over n squared is going to converge, but it's not going to converge by the alternating series test. Because this numerator is just -1, that means it actually doesn't apply to this test. Now, there are some other ways that you can get, there's actually a typo in this formula. There are actually some other ways that you can get the behavior of -1 to the n. And the most common way that I've seen in textbooks is with cosine n pi, because if you evaluate it for n equals 0, you get 1. Cosine of 0 is 1. And then cosine of pi is -1. And then cosine of 2 pi is 1 again. And then cosine of 3 pi would be -1 again. So cosine n pi is very common. Sine, this actually should be pi n plus pi over 2. If you have multiples, odd multiples of pi over 2 inside your sine function, you will also get -1 and then 1 and then -1 and then 1 and so forth. So this one is much less common because the formula for it is less compact than the cosine case. But if you see one of these, you should also be thinking about it in terms of this might be alternating. Again, double check the specific formula, because if it's not correct, if it's not done correctly, if this is just n plus pi over 2, this in fact is not alternating because the pi is missing. But double check the formula, because it might be just a disguise for an alternating component. It has to be exactly -1, 1, -1, 1. Otherwise, it doesn't apply. If it's just a sine or a cosine, like cosine n or sine n, then it's oscillating between -1 and 1, but it won't have all the sort of strong positive and negative properties that the strictly alternating sign series will have. So that is one other thing, particularly this one, to think about when you see these alternating series. An expression that has this in it is in fact alternating.